Have you ever noticed how some deep learning models can perform incredibly well on training data, only to stumble when faced with new, unseen information? It is a common challenge, and thankfully, there are powerful techniques to address it. Many deep learning models benefit significantly from L2 regularization, particularly those with a large number of parameters or when working with limited training data. This technique is especially useful for preventing overfitting, which occurs when a model learns the training data too well, including its noise and outliers, making it less effective on new examples. The core reason L2 regularization is so effective lies in its mechanism of penalizing large weights. In essence, it adds a term to the model's loss function that is proportional to the square of the magnitude of the weights. This penalty encourages the model to prefer smaller weights, effectively distributing the importance across more features rather than relying heavily on a few. This process, often referred to as weight decay, nudges the model towards simpler solutions, improving its ability to generalize from the training data to unseen data. It is a critical tool in managing the bias-variance trade-off, aiming for a sweet spot where the model is complex enough to capture underlying patterns but not so complex that it memorizes the training set. To determine if L2 regularization is needed, observe your model's performance. If you see a large discrepancy between training accuracy and validation accuracy, with training accuracy being much higher, your model is likely overfitting. Implementing L2 regularization involves adding the weight decay term during optimization, typically by setting a hyperparameter, often called lambda or alpha, which controls the strength of the penalty. Experimenting with different values for this hyperparameter is key to finding the optimal balance for your specific model and dataset. A fascinating insight into L2 regularization is its close relationship to ridge regression in linear models, predating deep learning. Its ability to create a more robust model by gently shrinking weights towards zero helps prevent any single feature or neuron connection from dominating the learning process. This leads to smoother decision boundaries and a more stable learning dynamic, especially in complex neural network architectures like convolutional neural networks or recurrent neural networks. Ultimately, applying L2 regularization judiciously transforms your deep learning models from mere memorizers into more thoughtful, generalizable predictors. By subtly constraining the complexity of the learned relationships, you empower your models to perform reliably and effectively on the diverse, real-world data they were built to analyze, leading to more trustworthy and impactful artificial intelligence solutions.